This is Astronomy Daily Live. Hope everybody's doing well. Hey, hey, welcome. Come on in. Come on into the circle. I'm just posting the fact that I am live now on various media. Let's see. I'm posting there. I'm posting there. Let's see if that actually goes. Yeah, that should go. I'm going to start up my live stream on my smartphone over here so I can monitor. Um, there's Uncle Bill in the room. Hey, hey, hey. Nice to see you, Uncle Bill. Hope everything's well in your world and everyone else's. Everyone else's. So yeah. Hey, the American Astronomical Society uh, meeting started. Conference. I don't know what it's called. Um, Started today. It happens twice a year. They have it in January and they have it in June. It's usually about the first week of each. And this year, the summer one, is, at least in the northern hemisphere, it's summer. This year, it's happening in Denver, Colorado, or Colorado, as they say. Um, And what I've been doing all day long, since I'm not able to attend, is I've been looking on Twitter at the hashtag AAS232. AAS232. That seems to be uh, at least one of the places to go. Now, the thing that I didn't do, and I probably should, is I need to see if the AAS has any recommended hashtags. So actually, let's do it over here so you can watch the fun for yourself. So let's go over to aas.org. Why do I have something that says CBS shows? That's a little weird. I don't know how that got there. I think I was looking at archive over here. So that's a little strange. Let's see. So let's see if the AAS has any recommended hashtag. It's so funny to see Kevin Marvel, who's now the executive officer of the American Astronomical Society. He was he was a um, uh, he was a grad student when I was a undergrad, and and uh, um, and so I knew him at the University of Arizona for I would say a couple years or so, and then he moved on. He went to actually NRAO, the National Radio Astronomy Observatory, and then I sort of lost um, touch with him. And I don't know, maybe it was a year ago or so, I learned that he became the executive officer of the American Astronomical Society, and it, that just makes me laugh because I knew him when he was just a silly little kid, and but having a great old time, and I'll bet you he still is, and it's just funny to see him in like a suit and tie there. That's something I never thought that I would ever see from Kevin. So yeah, hope he's doing well. I need to give him a poke. Uh, I don't even know if he would um, remember me. So, but who knows? So anyway, what we were over here was to look and see if there's any mention of any eggs that should be used. As I said, I've been using AAS 232, and that seems to have gotten, yeah, there it is. Okay, hashtag AAS 232. So yeah, that is the one to follow. So I've been doing that today, and yeah, nothing nothing too extraordinary. I wonder if it makes a difference if I do hash AA. I'll do capital AAS 232, just like what they have it there. It doesn't look like it. It doesn't look like it. It looks like it doesn't particularly matter. So we'll look at the latest postings. This one lady, Nola Taylor Red, uh, Twitter account Nola T Red, so that's NOLATREDD. She's been posting quite a bit. The Startorialists are there, showing off their art. That's another organization that I reached out to. I reached out to them and said, "Hey, you know, I've got artwork," and they said, "Cool, that's really really awesome. Let's hook up." And I wrote back saying, "Cool, let's do it." And that's all I heard from them. So it's a weird I seem to fall into. I don't know if it's just me or what, but anyway. So Nola Taylor Red has posted here, as you can see, you know, the star Taurus Nola Taylor Red right there. I was looking at the wrong Twitter feed. So most of the time, these conferences, you know, there are simultaneous talks going on. So that's probably what's here. So of course you can't be, you know, 2 or 3 or 4 places at the same time. Let's see. Let's see if we can look at the schedule here. See if there's anything interesting. Always some interesting things going on at the AAS. But interesting things that I noticed from the last AAS in January. No podcaster even, I don't even know if they mentioned it. So that was a little strange to me because the AAS meeting is you know, a pretty big deal. Pretty big deal. But yeah, this is taking this is taking a little bit too long. Too long today. I have, oh, there it goes. I have no patience. Is that all I'm getting? That's all I'm going to get? Okay. Okay. Yeah. Monday, June 4th. Here we go. Okay. So, yeah. See, so as you can see, there are multiple talks going on at the same time. Right? Like, you know, 6. Yeah. I don't know. Quite a few. I guess not that many. Oh, no, no, wait a minute. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 10 talks going on at the same time. Oh, some of those are poster sessions, so not all of them are talks, I guess. But here's at least 6 that are going on at the same time in different places. So, you know, that's one of the things that you got to do when you go to a conference, right? Especially like this, you have to get get that schedule early so you can figure out where you want to be uh, when. Yeah. So anyway, that's a great way to keep track of what's going on at the AAS meeting. Is just look up hashtag AAS232, and anybody who uh, puts that hashtag in their post, you will see it, and you can sort of keep track of what's going on there. I guess there are some um, um, press conferences that are going to be live streamed as well. So I don't remember. I don't remember exactly where that link is. I had it here. Yeah, but look around a little bit, see if you can find that. Let's see, publishing, divisions, careers. Oh, this is just AAS in general. Okay. Registrant list, undergraduate orientation. uh-huh. Those undergraduates just obviously just are completely lost, right? I don't know. I was an undergraduate. I never went to a AAS meeting, but I went to a number of other ones. And you know what? I was never confused. I never needed any kind of orientation. So I don't know what that's all about. So I think I think we want to coddle our students a little bit these days, and maybe I was part of the last generation that really wasn't, right. That was sort of uh, you know, be like, oh, you want the answers? Well, go go find them. Go get them. And 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 if it's too hard, well, maybe you shouldn't be doing it. So yeah, I don't know. Let's see. Hello, Tom. Hello, Bobby. Nice to see you all in the chat. So yeah, I guess you know, this is just a fun, casual, laid back, astronomical type of live stream happening every single day, starting at 2 hours UTC. I've got my hydrogen hydroxide today, HOH. So cheers. Mm, freshly brewed. Mm, pretty nice. Pretty nice. So I guess let's you know, I posted a link to a paper that I found over at Archive today that sort of seemed a little interesting. And so, you know, it's always way too much uh, to try to go through these things in any kind of extreme detail. But you know, I like to just sort of show you things that at least seem interesting to me. And so I was scanning today's archive, the astrophysics archive. This is the, you know, the bleeding edge of astronomical research. This is the stuff that's being reported. Now, obviously, this isn't really the stuff that's going on right this very moment, but this is the work. These are the results that the astrophysics community has decided to let loose into the universe and see where the chips fall. And you know, scientists love to share information. They love to as soon as they make some kind of discovery or write some kind of code that does some kind of interesting model or you know whatever else, they want to tell everybody, right? And that's a good thing because that's how science gets done, right? I mean, if you sort of keep everything to yourself, then no scientific progress can be made. But I was going through these, and there's some, moderately interesting ones. I sort of lean towards the observational side of astronomy. That's yeah, that's a bit of a bias, but I'm also, I'm also trying to make this, moderately interesting to those of you who are here, and not bury you too much in uh, what becomes, just mathematical insanity. So, and plus, the mathematics, going through a paper that's, heavy in the math, um, I would really need to take some time, right, to understand uh, going on with all that. Just even to just barely be able to talk about it, right? But this one here caught my eye. Where is it now? Oh, I completely go by it? I think maybe I did. Let's go down again here. I didn't think I was that far. There it is. So, Phlegethon, Phlegethon, a nearby 60-degree long retrograde stellar stream. So I thought that was kind of a interesting title, and I'm going to pull up the paper here, and the abstract is the thing that sort of grabbed me, right? Sort of grabbed me. So they report on the discovery of a 60-degree long, I mean, that's in the sky, 60 degrees long, long stellar stream in Gaia Data 2, Data Release 2 catalog, found using the new Stream Finder algorithm. The structure, which is probably the remnant of a now fully disrupted globular cluster, lies approximately 3.6 thousand parsecs away from the sun, um, in the direction of the galactic bulge, and possesses highly retrograde motions. So retrograde, meaning that all or most of the material that is moving in the galaxy is moving one particular way, and this stream, this um, stellar stream, the objects, in this case stars, probably other stuff too, I would think, but we can just see all the stars, is moving in the opposite way, so highly retrograde. So we find that the system orbits close to the galactic plane, um, at galactocentric different distances between 4.8 and 15.4 thousand parsecs. The discovery of this of this extended and extremely low surface brightness stream, 34.6 magnitudes per square arc second, um, with a mass of only 1,180 solar masses, demonstrates the power of Streamfinder algorithm to detect even very nearby and ultra faint structures. Due to its proximity and length, we expect that um, Phlegethon will be a very useful probe of the galactic acceleration field. Now, before we move on, I have just been summoned by my owners to open this door because see the thing is they don't have any thumbs. So without thumbs, it's pretty hard for them to grasp a handle. They know what the handle is and where it is and what it does, but they can't turn it. So they have to summon me. So I'll be back in like 10 seconds. Hold on. All right, there we go. Hello. My job is complete. I have been praised and thanked, and yeah, I just feel so much better now. So, yeah, and I think the other cool thing, of course, about this is that they are using um, the Gaia database to do all of this, and then some kind of a sophisticated algorithm to figure out uh, what stars they want to pull out. So the Stream Finder works by examining every star in the survey in turn, sampling the possible orbits um, consistent with the observed photometry and kinematics, and finding the most likely stream fraction given a contamination model and a stream model. Okay, interesting. Anyway, as with most of these things, I just like looking at the pictures. I think the pictures are uh, fascinating, right? Oftentimes, at least. See, now when I want this thing to work, it doesn't. Okay, I'm going to zoom out a little bit so we can see these pictures a little bit more. So these are two plots, um, pretty much of the same thing. They've weeded some stars out in this bottom one compared to this top one. But what they're plotting here is galactic longitude, which is this like a cursive L, and galactic latitude, right? So the center of the galaxy, of course, is at 0, 0 right there. And then as you move this way, you're sort of moving east longitude. Here's west longitude that way, right? So this line, right, at 0 degrees galactic latitude, um, is is the galactic disk, right? Yeah. I mean, it's the uh, um, center line of the latitude. Um, and as I said, the stupid thing. So that's showing positions, right? And then the colors are showing velocities, right? So the the yellow here is, and I guess this is a tangential um, velocity, right? So there's a radial velocity, which is how fast the object and us are moving towards one another, right? The tangential um, velocity is 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 the motion right angles to the radial velocity. So basically moving sort of across the sky. And what they find, right, is that there's these guys who are yellow over here, and they're not moving much at all. And then you've got these pink guys here, which are moving what about 200 kilometers per second. And then you've got these blue guys here. There's some here, and there's a little bit here, and there's here, right? That are moving um, at 400 kilometers per second. Um, so yeah, they've just in this bottom plot, right? They've just said, okay, let's just show all the stars that are moving at 250 or more, right? So that's just these guys, and yeah, that's sort of that shows kind of an interesting some interesting patterns here, right? Kind of interesting pattern that does indeed, right, go from about 0 degrees and swings around to almost 60. Wow. Wow. Sort of lined up with the galactic disk, though, right? Sort of lined up. There is a projection thing here, too, because we're projecting a sphere onto a rectangle. I'm thinking that this curved line probably isn't curved. It's actually a straight line. But that's kind of interesting. So there's this one here, and there's this one up here too, right? So yeah, I mean they're it looks like they aren't looking at stars, um, you know, plus or minus 30 degrees of the galactic plane, which makes sense because there's too many of them, right? There's just too many. But these they're calling streams. Streams, huh? So there's a bunch of other plots here. This is showing, um, zoom in a little bit here. So this is showing the the motion of those stars, both in right ascension and declination, right? So um, these things all seem to be moving sort of toward, oh, I'm sorry, not right ascension and dec, but galactic longitude and galactic latitude, okay, in milli-arc seconds per year, thousands of an arc second per year. And it looks like, a lot of them are moving moving east. I guess moving east, is that a negative one? I'm moving negative longitude. Yeah, I think that's moving east. Um, but yeah, another interesting structure here because, yeah, well, kind of hard to interpret this kind of a space, but then they're also showing it relative to galactic longitude, right? So these red ones here are high galactic longitude, and these blue ones and purple ones here are low galactic longitude. So the ones that are moving um, the fastest, right, are the ones, I don't know, looking at the colors here, it's almost um, kind of hard to tell. Let's see if we zoom in a little bit more, if we can see a little bit more color. I want to be able to see those colors. I don't know. It sort of looks like a mixed bag, but it's almost like these guys are moving, relatively speaking, right, slower, at least in galactic longitude, than these guys are. But these guys are at low latitude. These guys are at high or longitude. These guys are at high longitude. So it's almost like the further away they are in longitude, yeah, that's a complicated plot. I'm gonna have to think about that one for a while. Let's see what else we got here. Sky distribution of the selection drawn from figure 2. Let's zoom in again on this one. Very clean stream-like structure is revealed by the proper motion selection. The proper motion distribution along the stream is galactic Musa L and Musa B, which of course are the proper motions in the longitude and latitude axes, are color coded on the top and bottom panels. Continuity of the proper motion distribution is directly obvious from the individual proper motion measurements. Okay. Yeah, all right. So here they're just doing like a color, or actually a color magnitude diagram from Gaia. This is a parallax distribution. So yeah, this is what they sort of think the orbital path of the stream is, right? Um, so again, this I guess, yeah, the 00, I guess 00 would be the galactic center, right? Describing the text was used to fit the full sample simultaneously, yielding the best fit orbit shown here. The XY plane shown on the left panel and the RZ on the right panel. Okay, all right, yeah. That's radius and of course the z-axis, the how high above or below the galactic plane this thing is. So the short red region corresponds to the area where the observed stream stars are currently located. The progenitor clearly stayed close to the plane of the galaxy on a retrograde tube orbit. In this Cartesian system, the galactic center is at the origin, and the sun is marked with a yellow dot. So that's where we are. Wow, it's pretty close to us then, right? So that's where we are, right? Because we're with the sun, right? Theoretically. Oh, let's get over here. That's too big. Okay, so here we are, and we're looking at this thing, and there it is, and this is how they think it's orbiting the center of the galaxy. And so this is as if we're looking down on the galaxy, right, from above. And then this is looking at the galaxy from the side. So yeah, that's kind of interesting, I suppose. I mean, that's uh you know, do you have enough data there to really be able to project these orbits? Yeah, maybe. Maybe. Let's see, are there any other pictures that, what is this here? Figure 7, comparison of the orbital solution to the best. So, okay, yeah, so this is how they're trying to figure out what the orbit of these things are. And so you can see that, I mean, yeah, you can do a best fit here. And that's what this dashed line is here, right? But the it's pretty noisy data, right? Pretty noisy data. Um, and they're showing that here. This is I really appreciate seeing this kind of data being shown, right? What you're seeing, excuse me, is, and it's kind of hard to see here, but you're seeing little red dots here and then these lines, right? Well, this is the measured position, and this is the error in that measurement, right? So, and then they've done a best fit to that, right? And look, it's not even 0, right? So um, they're calculated sort of residual errors from their fits even have an interesting bias. So very cool though. So yeah, they're trying to figure out what the orbit is, and that's kind of neat. So we present the discovery of a new stream structure that we've named Phlegethon. Phlegethon, which lies close to the sun. Yeah, I mean um, that's uh, that's about 10,000 light years, so that's pretty close. Um, highly retrograde orbital motion um, to ascertain whether a phlegethon could be related to any surviving globular cluster. In figure 8, we compare the orbital properties of this stream with the globular cluster sample recently analyzed. We have labeled certain well-known retrograde globular clusters. Phlegethon clearly has extreme properties with only. So let's look at figure 8 here. I didn't see figure 8. Okay, here we go. Is this figure 8? Yeah. So yeah, it's that's sort of, I don't know, these, I guess these are the retrograde ones, right? These are the retrograde ones, the ones that have a positive LZ, I guess. The galactic globular cluster whose orbits measured by Gaia are shown here in the LZR periplane. It's some kind of radius. Retrograde objects have a positive LZ, right? So, I guess the only thing we can really say here is that, I'm sort of seeing a V shape here, right? I mean, it sort of falls apart here, but, if you sort of see a V shape here and you extend this out, well, that goes right there and that goes right there too. So, yeah, maybe it's not so unusual. It's just that things haven't been observed out there. But yeah, it doesn't look like. Let's see. Most importantly, however, this analysis indicates that there are no known globular clusters with similar dynamical properties to this stream. So the progenitor has probably not survived. So I don't know why they're thinking that this is like uh, a globular cluster that's been disrupted. I'm not quite sure where they get that guess. Continued orbiting in this disk-like but retrograde manner until the present day. It's striking then that the population appears smoothly distributed on the sky, despite having been bombarded by dark matter subhalos over the last 10 billion years. Um, it may prove very rewarding to hunt over the sky for stars with similar orbital properties. This would increase the lever arm for orbital fit analyses. Yeah, of course. The detection of Phlegethon shows that the Streamfinder algorithm can be successfully employed to find even nearby structures of exceedingly low surface brightness. So far, the present contribution, we've analyzed only a small part of the parameter space of possible stream structures. Our next efforts will focus on expanding the search criteria and trying to explore further these fossil remnants in the Milky Way. Pretty cool. Pretty interesting. Cheers. Cheers to Phlegethon. Phlegethon. Cheers to Phlegethon. Woohoo!
kind of interesting. I guess probably what we should do is dive right into let's do an object of the day. So let's go into the NGC catalog, the new general catalog, which is mostly non-stellar objects. So that's anything that isn't just a single star. So like a globular cluster, an open cluster, a uh, a galaxy, a planetary nebula, and a gaseous nebula. Now, some of the objects in the NGC catalog are actually stars. Hey there, Hip. Nice to see ya. Nice to see you. Lurk away. We're just going to look at some new general catalog object. So, in the new general catalog, there are 7,840 targets. And as I said, some of them aren't, well, some of them are stars that have just been misidentified. Hey there, Totterbert. Nice to see you in the chat. Um, so yeah, let's take a look and see. Let's see what we're gonna learn today. So I'm gonna choose an integer here using random.org between 1 and 7840. So let's see what NGC object we're gonna look at tonight. Hopefully HST will have looked at it too, because then I can make a picture. All right, here we go. Ready? Drum roll, please. 1436. All right, so let's go over to Simbad. And 1436, right? Is that NGC 1436? Now, the NGC numbers are ordered by right ascension, right? So 1436, let's see, 1436 divided by 7840 times 24, that puts it at about 4 hours 23 minutes, something like that. So yeah, that's well, it you know this just tells us RA, right? So it doesn't tell us anything about declination. But that right ascension um, is going through like Taurus and Gemini and those kinds of places. And there are a lot of clusters over there. So I'm wondering if NGC 1436 isn't some kind of cluster. Now, most likely, I think most of the NGC objects are galaxies. There's just a lot of galaxies, right? But I'm wondering if this is going to be a cluster of some sort. And yeah, it's going to have a right ascension of, somewhere around like 4 hours or so, I think. Let's see what it is. Nope, it's a galaxy. It's a galaxy. All right. So right ascension, well, close to 4 hours. So 3 hours, 43 minutes, 37 seconds, and a declination pretty low, negative 35 degrees at 51 minutes, 10 seconds. So this is a spiral galaxy, C class, which means that the spiral arms are pretty open, and yeah, you can sort of tell. I mean, you can definitely tell there's gaps here. Let's see. Does the Sloan Digital Sky Survey see it? No. Okay. So, oh, pretty pretty bright as far as galaxies go. Um, the B and the R are sort of visible wavelength filters, JH and K are more towards the infrared. So definitely brighter in the infrared, right? These numbers are smaller than these. So brighter in the infrared sort of implies that this galaxy is, leans towards the red, not necessarily red shifted, but um, just a lot of redder objects, which further implies maybe they're a little bit older, right? So let's see. There's probably a bunch of different names. Yeah, a bunch of different names. Pretty cool. Kind of interesting here. So it's NGC 1436, and look, it's also NGC 1437. What is that all about? I don't know. We will try to find out. So not a lot of references, not a lot. I mean, in the past 20 years, there's been 48. So yeah, not a very heavily studied galaxy. All right, let's see how far away we think this little galaxy is. Well, I'm not seeing like all measurements. All right, so 15, 17, 18.6. So let's do an average here. 15 plus 17.06 plus 18.59 divided by 3. So averaging those three, you get 16.88 megaparsecs, MPC. So 16.8 times, so a megaparsec is 3.26 million light years. So this galaxy, on average, right, average measurement is like 500 million light years away. It's 550 million light years away. Is that right? No, sorry. 55 million. 55 million light years away. So, yeah, that's actually pretty close. Pretty close. And you can sort of tell by the radial velocities here that, yeah, that's more or less the same, right? More or less the same. So pretty consistent. We and it are moving away from each other pretty rapidly, right? Probably about 1,300 kilometers per second or so. So we're hustling through. Let's see. Well, let's do this. Let's see if HST has looked at this, which is unfortunately sort of unlikely. But yeah, let's look anyway. And we're going to select everything, every possible piece of data. So NGC 1436. NGC 1436. Now, it's extremely unlikely that we're going to find anything, but let's try anyway. Oh, we did. Actually found NGC 1437. Now, I'm a little confused about that. So let's go up really quick and see what is going on here. Why are there two names for maybe the same object? A little confused. This thing is taking its time loading. Well, I don't see any galaxy nearby. I mean, there are galaxies nearby. See, there's these guys. Wow, that's a nice little cluster there. But why? But why would this be called 1436 and 1437? I don't know. I don't know. But look at this. Back in 1995, 1437 was observed uh, twice. Same filter, same exposure time, same instrument. So we're not going to get any color pictures or anything, but let's take a look. Yeah, well, that's pretty nice. That's pretty decent. What, that was a 80-second exposure? Yeah, 80-second exposure. Let's let's look at the proposal here. Let's see what they were up to. So this is just a proposal abstract, right? We're not reading the entire thing. So striking results have been obtained from HST images of the cores of nearby galaxies. The near diffraction limited HST PSF is uniquely suited to identifying compact structures. So far, HST observations of nuclei have been largely of elliptical galaxies and a few of the nearest early type spiral galaxies. The nuclei spiral and S0 galaxies are likely to prove as interesting as those of the elliptical sample. We propose a snapshot PC um, imaging survey of a subset of a nearby redshift and magnitude limit sample of 200 disk galaxies to characterize the nuclei of galaxies over a broad range of Hubble types and luminosities with a variety um, of environments. These data will provide invaluable statistics on the presence of nuclear cusps, stellar condensations, interstellar disk and dust lanes in disk galaxies. The properties derived from nearby normal galactic nuclei will also provide a reference set for studies of rare objects such as active um, galactic nuclei. Furthermore, the archival database of such observations will be a resource for more detailed studies of galactic nuclei in later HST cycles. This program is the continuation of cycle 3, blah, 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 blah. All right, so they are looking at the centers of these galaxies, and that's why they have um, the center of the galaxy inside of this of this little box in with pick 2. I forget exactly what the characteristics of that box are. Maybe it's higher res in the middle here. I'm not remembering exactly. I mean, in this image, we're overexposed, right? So yeah, don't know what's going on. Don't know what's going on there. This is just a um, like a JPEG image of the actual data. See, so we could actually grab, the actual HST data in FITS um, format, um, and then we would be able to um, um, most likely, play with the brightness and the contrast to see if indeed the center is overexposed or not. It probably isn't, right? They have to make these with some kind of a stretch. Um, but yeah. Now, I think, oh, man, I'm going to get myself into trouble. I do have Fitz Liberator on here. Okay, all right, here we go. Let's do it. Oh, um, preview in Fitz format. Can I do this? It's want to be able to preview search. That doesn't look right to me. Interactive display. What does this do? I was going to download the FITS file, but it's not. It's not. It's not letting me do that. Play with it this way, but that's not what I want. I want to be able to grab the FITS file, preview in FITS format. Huh. I wonder. Yeah. Yeah. For some reason, I'm not able to grab that. Let's There's another one, isn't there? Let's look at this one. Grab this one. It's going to do the same thing. Dang, how do I get the FITS file? That makes me mad. It makes me want to have a fit. Hmm. Dang, I should be able to do that. Let's see. See over here. Oh, went too far. Oh yeah, that's where I wanted to go, right there. Is there a way just to grab the FITS file? It doesn't look like it. Wah. Right. I'm pretty stubborn. I like to try exceedingly hard to get what I want. Making me mad though. Hmm. Hmm. Let me try it on my Linux machine here. That's not gonna. I know that's not gonna help you folks at all, but I'm kind of curious, well, as to why I can't seem to grab the FITS image that I want. So NGC 1436 is what I'm gonna call it here. Sorry, you're not seeing all the action. So all of that, all of that, all of that. Search, data set, review, preview in FITS format, and it's doing the same thing. Okay. Well, at least we get a relatively interesting, decent view there. I sort of, I mean, this is at least in the proximity of a pretty cool looking cluster. Look at this barred spiral galaxy here. Oh yeah, it did it for us. Oh, probably zoomed in too far. Yeah. That's pretty nifty looking galaxy, right? So that's called a barred spiral galaxy because it's got this what looks like a straight bar across, and then the spiral arms come flinging off of that. But you've got some others in here too, right? You've got a bunch of elliptical galaxies here, and I think this is our guy, right? If I remember right. Yeah, yeah. So that's kind of interesting. looking though. Do you see these? Yeah, kind of interesting structure there in the spiral arms. Don't know what's going on with that. Let's go back to the list of papers and see if there's anything that pops out here. I like that these are ordered by date, right? So the earliest ones are up at the top. Galaxy groups, classical morphological analysis of galaxies. Who were these guys? Arth Illingsworth. So let's look in the paper list and see if Illingsworth. No, didn't even publish a paper on this. What the heck? There are. It looks like there are some papers referenced though. Quite a few of them, right? Quite a few, but and this goes in the opposite order. So I'm not sure how this is related to this particular object. Not quite sure. Does it say up here? Papers referencing 5446. Okay, well, that's just that. That's kind of a weird way to do things. Oh, Illingworth, not Illingsworth. Illingworth. Do Illing. Nope. No Illing. Huh. Okay, well, never wrote a paper. Got 160 seconds worth of HST data. Never published a paper. Or it's somewhere else. Who knows? Who knows? Cosmic Flow 2, Herschel Fornex Cluster Survey. 2M++ Galaxy Redshift Catalog. 2 micron all sky survey. That's 2 mass. There was a 2 mass image, wasn't there? Oh, I guess that's up here. Let's look at the 2 mass image. Okay, that's not incredibly exciting, but look at it anyway. 2 mass. Look, they've got Gaia data release 2 now here. That's pretty cool. Okay, so that's just showing points. That's pretty useless too. Okay. Gaia data release 2. There's a couple of located stars there. All right, well, just your typical spiral galaxy. Nothing too exciting. I guess somebody looked at it with HST to sort of understand the structures of the centers of spiral galaxies, but didn't seem to publish anything on it. So who knows what that's all about. I guess he didn't necessarily have to be the primary author. But yeah, you'd think that, yeah, see, nothing prior to 1998 is in here. So yeah, maybe it was published prior to that. Let's, you know, as I say, I don't like giving up. So let's just look at archive.org and see if that name pops up as an author. I don't like giving up these kinds of searches if I don't have to. Come on. So we'll punch in Illingworth here and we'll look under authors. See if anything pops up. So this guy is Garth. So that would be a G.D. Illingworth. So he published something, looks like just last year. Very low luminosity galaxies in the early universe have observed sizes similar to a single star cluster complexes. But let's go back to, who knows if this is gonna, I don't think, I don't know if there's any papers back in 1995. No, this only goes to 98. Oh, there's a 97. 97, 96. So Keck spectroscopy and HST imaging of field galaxies at moderate redshift, and he is one of the authors here. And faint field galaxies previously imaged by HST with PIC2. All right. Well, let's see if this has these HST images in them. So he was a co-author in this paper. And let's just see if there's any pictures of the HST data that we just looked at. HST imaging, well, don't see much. Sometimes these images are at the ends of papers. Not seeing much. Individual galaxies. They just make comments, figure captions. Where are they? That's not very nice. So yeah, I don't see any pictures here. Wow, that's no fun. That's no fun. All right, well, there's only so much digging I can do until I'm just out. And it looks like I'm out of time too, so I don't want to drag this out too much. It's a pretty nifty looking galaxy though. Gotta say, right? Pretty cool looking galaxy. Pretty nice. Can't complain about that. Lots of interesting structure here. I'd like to take some longer exposures and see what's going on, right? There's pretty interesting stuff going on in here. So yeah, pretty cool. All right, well, I guess I'm going to get out of here for now. Let me stop sharing my screen and bid you all a good evening, a good day, And yeah, we will do this again tomorrow, same time, same place. As I said, this is a very casual, um, open-ended, fun thing where we're just, you know, talking and thinking astronomy, whatever it is. Sometimes we run into dead ends. Sometimes it's extremely interesting. That's how science goes. Sometimes it's interesting, sometimes it's not. So yeah, hopefully there was a little bit of enjoyment there. Learned a little bit. I always learn something on these things. Um, so yeah, I think it's totally awesome. But all right, I'm gonna get out of here for now. So have a great evening, great day tomorrow, and peace, cheers, and all that. I'll see you on the spin tomorrow, a little less than 23 hours from now. All right, take care, everybody. Bye.